usually before the first exams we discuss here. By the final exam, it's like previous semester, it's always crowded. So some of you didn't take physics 1 with me, so let me just quickly tell a few words about how the exam works, right? So the exam is in only one video where we have our lectures. So usually just you wait outside until we prepare the room, we distribute the exam papers, right? And then we let you in, and then we start. The format of the exam. Okay, better. Format of the exam is exactly the same from semester to semester. The previous year exam is in the blackboard. Is it loud enough or too loud? Okay? So the format is exactly the same, and I posted previous year exam 1 and 2 already in the blackboard. Formula sheet will be attached to the exam paper. So you can disconnect it, and then after the exam you can trash the formula sheet. Right? And the formula sheet you can see again in the blackboard. I posted it there. So 3 big problems for 20 points, and then there will be for 20 points 5 multiple choice questions. Right? About the problems, so the major points, the major parts of this semester, definitely there will be a problem on Gauss's law, just 100%. There will be a problem on the Gauss's law because it's one of the fundamental equations in physics overall and in electricity and magnetism. Right? It's one of the Maxwell's equations. So usually I emphasize on that. Right, and the rest, it depends. It depends. What?
I was just stretching.
Yes, stretching. Okay. What else? What else? The final sort of cut in terms of material will be, so in the previous week, we introduced the electric potential energy. So there will be a problem on electric potential energy. Electric potential, no. All right. In my recitation classes, I haven't started discussing or practicing potential energy, right? But we will do it on Tuesday, right? And the idea is exactly the same like in physics 1. Just the potential energy is of a different nature, electric potential energy. Otherwise, it's exactly the same idea. So we will practice that, and we will practice today. Okay, I think should be enough. Any questions about the exam in general, format, and so on? Okay, so now let's start reviewing first major ideas. Let me turn on this thing. So first, we started with Coulomb's law, and let me do this. All right, so let's assume that we have a point charge Q capital, and let's assume that we have some charge Q. They can be positive, they can be negative, no restrictions. And if distance between them is r, some arbitrary distance r, then of course we can introduce a force between them, which is described by Coulomb's law. So K Q small Q capital over the square of the distance between them. Again, it's one of the fundamental also laws, but it's not part of the Maxwell's equations. So that was our first equation. And then recently, for the same system, we introduced potential energy. All right? We introduced potential energy. And both of these quantities, force and potential energy, let me write potential energy. Recently we introduced U equals K, Q, Q, and first power of the distance between these two charges. So potential energy and force, both of these quantities describes interactions. So that's why I put them all together. Right? So what's the fundamental difference between them? That is a vector quantity. This is a scalar quantity, right? So this is, strictly speaking, it's a vector. Of course, I wrote it in a absolute. It's a magnitude of the force, right? I wrote it this way, but of course it's a vector quantity, and that is a scalar. Okay, so let me write. This is electric PE, potential energy. All right, and this is of course Coulomb's law. Coulomb's law. Then what else? So let me separate this quickly like this. Then we also introduced the idea of the electric field. E equals. How did we introduce the idea of the electric field? You take the force. First of all, you take a small positive probe charge, put it in the field, measure the force, and divide it by the value of the probe charge. So F divided by Q, right? So that's how we introduce idea of electric field. There are no any special units. Electric field. Now, if you have a charge which is exposed to the electric field, given electric field, how can we find force acting on the charge? Let's say here we have electric field, we have a charge. How can we find force? QE, Q times E. That is another one of the fundamental equations which will be added to the set of Maxwell's equations closer to the end of the semester. Right? Again, you can easily get it from here. F equals QE. Right? So then also we can write that F equals Q times E. One of the most important equations in physics, electric force. Now, next we introduced a parallel plate capacitor. Now let me get properties. Which way I drew it? Negative here, positive there. Okay. Right, so a parallel plate capacitor. So minus, 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 and here let's say plus, 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 plus. Electric field lines start on pluses. They start on pluses and then on minuses all the time. It's a consequence of the fact that we use a positive probe charge all the time. So the electric field this way, right? So this is electric field. And the expression for the electric field, let me write it here. So electric field, first of all, electric field is constant, right? It's constant. And it is equal to eta over epsilon naught, and it's constant. What's the meaning of eta? Charge density. Charge density on the plate. Okay, then we introduced recently the electric potential energy. So if you take charge Q inside, if you position charge Q inside, in order to have, in general, potential energy, how many objects you must have at least? Two, right? Because you must have at least two objects because they must interact, right? If there is nothing, there are no objects to interact, and of course potential energy is zero. Right? So let's say this is coordinate system. This is D, and then potential energy of this object is U equals QES. Potential energy of a charge inside of a capacitor. So in this case, charge interacts with a capacitor. So potential energy of Q in a capacitor. So that is the formula for potential energy of 2 point charges. That is the potential energy of a charge inside of a capacitor. We just recently introduced this. Let me check what else I missed. So it should be enough about capacitor. Yep, electric potential we're not going to discuss. Okay, so after this, we introduced Gauss's law. Let me separate it like this. So now, Gauss's law. Right. Fundamental law which works at any point of the universe, at any moment of time, no restrictions whatsoever. Really universal, real law. So if you have a set of charges, let's say Q1, Q2, Q3, Q4, 5. And the first step, when you want to apply Gauss's law, what should be the first step? You need to pick Gaussian surface, right? You have to pick a Gaussian surface. So let's assume that, for example, this is our Gaussian surface. Of course, this Gaussian surface must be closed. If it's an open surface, you cannot apply Gauss's law, it just wouldn't work. And so, Gauss's law, it's integral over this closed Gaussian surface, E dot dA, of course, over Gaussian surface, equals to Q enclosed over epsilon naught. One of the Maxwell's equations. So far, no one managed to find a place or examples where this doesn't work. So until that moment, this is a universal law. If you can find some example where it fails to work, okay, you will be famous, right? You will change the foundation of physics, right? And of course, Q enclosed, you remember, it's a total charge, net charge within your chosen Gaussian surface. You can pick any Gaussian surface. You can pick it like this, like that, whatever your goal is in your problem, you can pick the most convenient Gaussian surface for your case. What? Ah, it's just talking to each other. Okay. All right, so what else? Yeah, probably I should write here. So in this case, Q enclosed, it will be Q1 plus Q2 plus Q3. And of course, if something is not clear in terms of what I wrote, in terms of my handwriting, tell something and I will clarify.
What does it say that on the top, E equals Q over epsilon naught equals what?
Q over epsilon naught, just a second, let me, this?
Yes.
Okay, it's not Q, it's eta, Greek letter eta. So it's sort of like an N, but with a long tail, which goes down.
What is it for? Yeah, what's it for?
Ah, okay. Since we've used it already so many times, I tacitly assume that you remember. It's a surface charge density, right? So we introduced lambda letter to denote linear charge density. Eta was the surface charge density, and rho was the volume charge density. Okay, so let me write it's a surface charge density. So you take total charge which is on the surface, divided by the area of the surface. Okay, so now then I need to include this. Okay, then, yeah, so let me ask you, what's the, how do we call this quantity on the left-hand side of the Gauss's law?
Electric flux.
Electric flux. Sort of simple understanding, simple meaning of the electric flux, it's a number of electric field lines crossing a certain surface. Right, so that is flux. So, if the question is about finding flux using Gauss's law, then finding flux is trivial. Just calculate the charge inside, divided it by epsilon naught, and flux is found. But if the question is about finding electric field, most of the time it's a painful problem unless you have a nice symmetry in your charge distribution. And that's what we've been doing, right? Using spherical symmetry, cylindrical symmetry, right? But in the most general situation, like for example that one, good luck with taking that integral. It will be really big. All right, so let me separate this Gauss's law. What's next? After Gauss's law, we started looking at conductors. Conductors. In which state? Electrostatic equilibrium. Right. So if you expose a conductor to some electric field or some other charges, right, you have to wait for a short period of time until that electrostatic equilibrium is reached. Right. So for that period of time before conductor reaches electrostatic equilibrium, inside of the conductor it's a mess. Those electrons start panicking, running around, right, trying to make what? Trying to make the electric field inside is zero. They will never stop. They will keep running because they would feel this electric force. If there is a non-zero electric field inside of the conductor, they will be pushed and they will keep running and running until electric field zero. All right? Usually it takes not that long. Right? Okay, so electrostatic or conductors in electrostatic equilibrium. Okay, I will just draw some arbitrary conductor and just write everything what we know. So first of all, of course, electric field inside is zero. Then, it's conductors. Underline this. Is it possible to have excess charge inside of the conductor? No. Actually, to some extent, yes. Near the surface, you can say it's inside, right? Okay, really inside in the volume, no. Excess charge cannot be inside of the conductor, right? Only on the on this exterior surface. If you, let's say, if this conductor is positively charged, so this positive charge will be on the surface only. Again, simple explanations. If you dump over here positive charge, of course they repel each other, they hate each other, because they push each other as far as it's possible, and of course the farthest point near the surface, by the surface. Then, what about the electric field outside of the conductor? Your lab work, perpendicular, right? Outside of the conductor, electric field is perpendicular. It doesn't matter how complicated surface is. In shape, electric field outside will be perpendicular. Okay. Conductors, and we're getting. It's almost over. Except for, I was planning also to write a general expression for the electric flux in the case of the flat surface and uniform electric field. So, electric flux, let me write underneath. Electric flux, phi, Greek letter phi. E dot A, right? So it's a in case of a uniform electric field and flat area. Right? How many ways do we know to calculate flux? Basically, how can we calculate the dot product? There are two ways, you remember? If vectors are given in a component form, it's one way. If you have absolute value of E and absolute value of A and the angle, it's better to use the other way of calculating flux. Okay, so let me write like this. So it's a EA cosine of angle between these two vectors, or EX AX plus EY AY plus EZ AZ. How can we find the correct angle between two vectors? Physics 1, I bugged you a lot about that, and I will keep bugging. You need to position tails of both vectors at the same point, right? and then the angle less than 180 degrees is the correct angle. Right. Okay, I think it's enough. Basically, that's what is going to be on the exam, right? So these and these are the last points in our material. Electric potential is not going to be on the exam. Yeah.
If you do the dot product solution, so cosine just doesn't factor into it, we don't need to do an angle.
Okay, you lost me. Of course you need an angle. Cosine of correct angle.
But down below where we get...
Okay. This and this formula will give you exactly the same answer, right? It can be shown. So in this, if your vectors are given in a component form, this will be the easiest way to calculate dot product. You can still go this. You can still use this. You can find absolute value. You can find the angle, but it will be significantly more complicated. In the second case, if components are given, then of course the angle is not needed. Okay. If you desperately want to still use the first formula, okay, go ahead. You can easily calculate all those magnitudes and the angle. All right, it can be done. It will be just longer. Right? Just by looking at the statement of the problem, you can easily make a decision which approach is better. Both of them will give you exactly the same number. It can be shown mathematically. Okay, anything else? Let's start looking at problems. So let's start with first simple conceptual or semi-conceptual questions, right? And then we'll get to more difficult problems. Something very simple. Okay. Let's assume that you have a uniform electric field. I don't like this marker. I think it's time to change it. Ooh. So, electric field. And very quickly, let's assume that we have a plus Q charge. Direction of the force. Formula QE. It takes some time for students, but usually by the middle of the semester, everyone remembers. QE, right? In this case, charge is positive, right? So F equals QE, charge is positive, so direction of the electric field gives you direction of the force. So the force will be along E. But if the charge is negative, let's say minus Q. So in this case, of course, you will have to write something like this. F equals to minus Q times E. I just write it like this in order to show this minus sign explicitly, right? So that you wouldn't forget about it. So direction of E, that, and because of the minus, direction of the force is going to be in the opposite direction. Right. Again, remember, be careful with charges. Look at the problem. If charge is positive, chances of making a mistake is less. Right. If charge is negative, you have to be careful. Because every exam I see plenty, not plenty, but some students make these very, very unnecessary mistakes. Then, okay, let's assume this situation. We have a charge, let's say Q. And, yeah, the length, the angle, blah, blah, everything is given. Static equilibrium. So the charge doesn't move. All right, and give me any direction of the electric force. This way, that way, okay. So let's say this is direction of the electric force. Is this charge positive or negative? if we decide to use his direction of the electric force? What did you?
Positive.
In this case, yeah, positive. But what if I don't want to use his suggestion? What if I pick this electric field? What's the value? No, what's the sign of the charge? Because again, just by looking at sort of mechanics of the problem, you can see immediately that electric force must point that way, because which forces act? Tension, gravity, right? And in order to have this electric force, and if electric field this way, charge must be negative in order to get electric force in the opposite direction, relative to the direction of the electric field, right? Okay, so it should be enough. Yeah, so it's a F electric equals QE, right? So from this formula, everything follows. Hello. Okay, you're walking better.
Huh?
Walking better and better.
A little bit.
A little bit. Because you don't need crunches. Crunches. Right. I broke my bottle. It's difficult to close. I know. So next, again, sort of conceptual question. Right. So let's assume that we have some. No, you know what? Let me follow the way. Right. So let's say we have a sphere. It's a piece of metal. All right, and let me position over here charge Q1 equals, I don't know, 5 coulombs. And here, let's say charge Q2, let's say, I don't know, 7 coulomb, whatever. I don't know why I picked odd numbers. Usually I like even numbers. Right. So this charge creates an electric field everywhere. This charge also creates an electric field everywhere. So what will be the net electric field at the center of this sphere? What will be the value of the electric field at the center of the sphere? Net electric field?
0.
0? Okay, of course 0. In my recitation class, I remember I gave a big pause, right? Give a chance to express opinions, right? Okay, why 0? Simple words, it has something like this happens. So this piece of metal, let's assume it's electrically neutral, has tons of free electrons. So these free electrons sees this electric field and this electric field, like an invasion into their territory, right? This electric field, of course, they start running like crazy, right? In certain directions, right? Some will run to these directions, in this direction. Some will run into this direction, and they will, of course, they will keep running and running until electric field will be 0. So you will have distribution of these negative charges, something like this. Of course, denser over here. And again, denser over there. Right. And here you will have some positive charges left behind. Right. So basically, this net electric field inside of the conductor will balance external electric fields. Right. Of course, the distribution of charges will be very, very complicated. But they will arrange themselves properly to make electric field is 0. Of course, you have to wait for a short period of time, maybe nanosecond, maybe picosecond, right? Because, yeah, electrons, they still have mass, inertia, and they still need time to travel, right? But sooner or later, electric field will be 0. Make sense? No. No? You're joking, right?
No.
Of course. Of course. Of course, right? All right. Then, okay, now let's calculate something. Okay, let Let me separate this. So now let me get some arbitrary shape piece of a conductor. Right. And let's assume it is charged. Q total. Give me some number. Any positive, negative, right? Okay, you were against, so give me a number for that. 20. 20? Positive, negative? Usually people give positive numbers, right? It's a Valentine's Day, right? Right? 20 coulombs. Why not? Then, let's assume that inside of this there is a hole, void. It's a three-dimensional picture, right? And let's position inside of this hole some charge, QH, and give me some number. Okay, all right.
42.
Something, okay, yeah, why not, right? Positive, negative?
Negative.
I'm speechless. Now we'll have to crunch the, that is positive, you give me negative, right? Sorry, disobeying.
Is that a 42?
Yeah.
Or 4.2?
42.
I said you could do 4.
Okay, no. First, you gave me, I wrote, right? So, this is piece of metal, and that is the hole with the charge inside. What, something not clear?
Is that QH?
42C. QH sub H. You can use something else, QR for example. H stands for hole. Okay, and you know the questions, we solve problems like this in our recitation classes, right? So the first question, part 1, what is the total, okay, let me use capital, right? So what is a total amount of charge on inner surface? And at this point, you should be able to answer it immediately, right? And of course, I will tell you I will ask you for justification, right? So what will be the answer? 10. On inner surface? It's difficult to get logic, possible, but anything else? But I like 10. It's not like 42, right? So, 0, 10, 0. I thought you were just
42?
4. No? What do you think? He just has a very creative mind, right? Okay, guys, all right. So why 42? Can you just justify it quickly? Or how can you prove it? Of course, on the exam, I will never ask you to prove it. If you just write the value of the total charge on the inner surface, I can buy it. It can be easily justified. Can you? No?
Because the inner charge is negative 42, and they have to...
Yeah, in simple words, of course, you can say this negative charge will repel electrons inside of the metal, basically, and those electrons will leave behind exactly the same amount of charge on the inner surface. Mathematically, how that can be proved? Apply Gauss's law. In our lecture we've done, if you pick a Gaussian surface just below this surface, right, flux will be 0, Q enclosed will be 0, and since we know that this charge is inside, so it means that somewhere else there must be plus 42 coulomb, and it can be only on the Gauss or on the inner surface, right? But again, in a simple word, simple understanding, just this negative charge. Thank you, the negative charge, right? Of course, we'll just repel electrons leaving, and those electrons will leave behind the positive charge, right? Plus 42. Okay, so now let me put these guys, positive guys. But by giving me a negative number, you created a positively charged surface, right? Positive side. All right, okay, so Q inner will be, okay, I will remove question mark, I just don't want to rewrite it, will be equal to plus 42 coulombs. Okay, of course, second question. Let's calculate now the total amount of charge on the outer surface. And again, I cannot tell exactly the distribution of these positive charges will be complicated, seriously complicated. But of course, the total amount will be plus 42. Right, so now Q on outer surface. Let's answer this question. So, what can be used to find this charge? Or maybe you can give me a number again.
-20.
Negative 20. All right, okay, we'll see. Which fundamental law can be used now to find this charge?
Gauss.
Gauss's law in this case, not exactly. What did we use in our recitation classes to solve problems like this? Huh? Louder?
I said the excess charge should reside on the exterior surface.
Okay, let me tell you. Conservation of charge inside of the conductor, physically inside of the conductor in the material. Okay, you see we have Q total. The charge, the conductor is negatively charged, thank you, right? All right, and throughout the whole process, we don't touch that conductor, right? There's no any leakages of charge, so that minus 20 coulomb is inside of the conductor. We cannot change it, we don't change that. Of course, the charges can move within the conductor here or there, right? But we know that the total charge is negative 20. It's like over here, we have what, like 30 students or 50 students, I don't know, right? All right, and if we close all the doors, right, so no matter when you look in this room, there will be still this 30 or 50 students, right? Maybe tons of you will be over there, right? Conservation of people in this room we can use, but in this case, it's a conservation of charge inside of the conductor, right? So let's try to use it. Conservation of charge. You know what? I will separate this. Right, so let's use conservation of charge in the conductor. Let's use this. What about this charge QH? Is it in the conductor? It is outside. It's not in the material, not in the conductor as a material, right? It's outside of the conductor. So we're not counting this. So where can this charge be? Inside of the conductor is impossible. One of the properties. Charge can be only on the inner surface and the outer surface. There are only two places for in the conductor for charge to exist. Right. So I can write Q total equals Q inner surface plus Q on the outer surface. Again, inside we cannot have them. We proved that using Gauss's law in our lecture. So this total charge. What?
Is the minus 20, is it only conductor?
Which one?
Q, yeah.
Minus 20? Yeah, it's our initial condition. We picked a piece of metal. And again, you know, thanks to whom, that charge, we charged it with negative charge, negative 20 coulomb. So just from the very beginning, we charged it this way.
So
Right?
the conductor is originally.
Yeah, conductor was originally charged. And again, during this process of this game, we don't change the total charge. Right? It stays inside of the conductor. Okay, agree about this? Okay, so now what? This is given, this we found, and that is what we need to find. Usually every time it's just the algebra. Okay, and since you gave me numbers, so I don't know what will be the answer. So let me just solve it for Q outer will be Q total minus Q on the inner surface. Okay, let's plug numbers. Q total is -20. This minus comes from the formula, right? We solve this equation, and on the outer surface plus 42 coulombs. Plus 42 coulombs. So if you solve it, you're going to get more than you predicted, right? So you're getting, oh my God, 62 coulombs, right? Girls give me such a huge amount of negative charge, right? Minus 62 coulombs. No? Let's count. Minus 62, it's, okay, let me show. It's on this, wait, on this outer surface, I can even now draw it. It will be minus, 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 minus. Negative 62 on the outer surface, on the inner surface plus 42, you add them and you will get minus 20. Right? Right?
Yes.
Yes. Right.
Does this represent a two-dimensional thing?
It's
or-
three-dimensional, come on.
Okay, yeah.
Yeah. It's a solid piece of a conductor and a void inside, basically. Right? I can't draw a three-dimensional picture. So we're looking at the cross-section, basically. Yeah.
That's what I was going to ask, if we were looking at a cross-section.
Yeah, basically it's a cross-section, right? Come on, drawing something like this in 3D. Right, I'm not a computer, right? Right? Quite often I give a problem like this just to check basically Gauss's law, conservation of charge, right? But again, this part you don't have to prove if you just write down the right answer for this part about inner surface. I can buy it. Still conceptual question. Okay, I still have on this part. And I can erase this. So let's assume that we have charge Q. Let's say positive charge Q. And then, just for fun, out of the blue, I decide to apply Gauss's law over here, and I will pick some cylinder. Three-dimensional picture for those who wanted to see 3D pictures. So I picked a Gaussian surface, or some surface, for example, not Gaussian, just closed surface. And let's say I ask you, what's the total flux, electric flux, through this closed surface? What's the total value of the flux? 0. What's the total value of the flux? Yeah, why not? Still thinking? Right.
8.
What?
8.
8? Wow, what a nice number. I like it. Guys, it's very easy for you to give me answers. All right. Okay, flux. Who said 0? Why?
Charge is outside of the surface.
Yeah. Very often, Gauss's law, not very often, yeah, if you want. Of course, if you don't want, you don't have to, right? You can apply Gauss's law to find the total flux, but of course, if your surface is closed. And we have a cylinder, which is a closed surface, so we should be able to apply Gauss's law. So again, the nature of the left-hand side of this of the Gauss's law, it's a flux. It's an electric flux, right? So if we apply Gauss's law for this surface, inside of this surface there are no charges. No charge, 0. Flux, electric flux, 0. Right? So, electric flux, and let me just rewrite Gauss's law, E dot dA, Q enclosed over epsilon naught. Q enclosed is 0, since there are no any charges inside. To make better understanding why flux is 0, look, this charge creates an electric field lines, right? Like this. And look, over here, and over here, right? So these electric field lines enter this surface. Over here, here, and there, the same lines leave the surface. So if you calculate everything accurately, so when they enter, electric flux will be negative. When they leave, electric flux will be positive. And if you add them up, you will end up with 0. Net electric flux will be 0 because every line entering this surface is going to leave it. While when it enters, it gives you, for example, negative flux. When it leaves, it gives you positive flux. If you add those numbers up, you will end up with 0. So that's the logic behind charges outside. We're not counting the Gauss's law. Right, so flux is 0. Electric flux is 0. Now, consequence of this very quickly. Let's say we have a surface and we have charges. Let's say plus 2 coulombs, minus 2 coulombs, plus 1 coulomb. What will be the value of the flux, electric flux? Divided by epsilon naught, right? So in this case, electric flux will be minus 2 coulombs, plus 1 coulomb divided by epsilon naught. So it will be 1 divided by epsilon naught by 1 coulomb divided by epsilon naught. Okay, so we refresh this. You shouldn't have any problems with problems of this type. All right. Okay. So now, we can erase this. Right. Oh, now let me position my Gaussian surface on just closed surface like this cylinder. Right, and electric field lines, why not like this? So this is E. And let's say this area is A, for example, right? Anything else? No, just A. And the electric field is given. So what will be the value of the total electric flux? Can you tell me the formula? Basically the expression, right? What will be the value of the electric flux through this cylindrical surface? What will be the value of the electric flux through the cylindrical surface? 0? You're so kind of afraid to say it. All right, 0?
Yeah.
Why?
Because it's totally parallel, so it's the same
Okay,
shape.
God's feeling tells you, right? Basically, again, the idea of the electric flux, it's a number of electric field lines crossing a surface. And these electric field lines are not capable of crossing this surface because they're parallel to the surface, right? It's sort of conceptual explanation. But what about mathematical explanation? How can we prove that the flux is 0 through the cylindrical surface? I asked you on purpose because of your question 10 minutes ago. I have a bad memory. I mean, memory for bad things, right? Right?
Well, they're all going in and then they all leave. So it's
Okay,
positive.
let's start. What is the direction of the area vector dA for this surface? Let's say I'll pick this small patch. What's the direction of area vector?
For the round part.
Yeah, for the cylindrical surface, right? For this area vector. Okay, people behind already pointing in the right direction. Right? Okay, the major property of the area vector. It's perpendicular no matter what to the surface. If you want to introduce the area vector for this surface, it's either this way or that way. But if you have a closed surface, like for Gauss's law, we introduce convention that the area vector points outward all the time. So perpendicular, area vector, this way. So as a result, what's the angle between the area vector and the electric field? 90 degrees. Cosine of 90 degrees, 0. Flux is 0. Right. So I can say that. Alright, so the flux through cylindrical surface equals to EA cosine of 90 degrees equals to 0, because cosine of 0 degrees, cosine of 90 degrees is 0. Right. Then, what about flux through, let's say, this surface S1, and then this will be my surface S2. What will be the flux through surface S1? Area vector this way, electric field that way, the angle between these two vectors, pi, right? Pi. So it will be EA cosine of 180 degrees. So it will be minus E times A. Flux through that surface, area vector that way. Okay, let me draw three-dimensional A. Now, area vector and the electric field vector are in the same direction. And the angle between them is 0. So EA cosine of 0 degrees. So it will be EA. What's the value of the total flux?
E times the area.
Carefully look through the whole list of our fluxes. 0 minus EA plus EA. If you add them all up, 0. Was it possible from the very beginning to tell the answer? Why? How?
Just by using the same formula faster.
Huh?
Just by using the same formula.
Basically using the formula. But what about if you want to use Gauss's law? Do we have any charges inside? No, so the flux must be 0, right? So of course you can say maybe this uniform electric field is created by gigantic capacitor, right? But those charges are outside of the surface, right? So the flux must be 0. Okay, so I just wanted to play with definition, not definition, yeah, actually definition of the dot product, right? So we can.
mõtlesid nii ja kindlaks tegid ka, no mida teha, kui see silmas ennast parandaks, nii tegid paberid ja jahipaadi jussid ma tean ju milleks, et ikka naisi jahtida.
So let's assume this situation. We have infinitely long cylinder with uniform volume charge density, ρ. And to make the situation more complicated, let's make a concentric hole which goes through the whole cylinder, right? So R1 will be radius of the hole, and R2 is the radius of the this surface. Right. So I will put a new bullet and right. Okay, I will write. So this is the problem about Gauss's law. Right. So let me estimate the amount of space I need. So that is my infinitely long cylinder of radius R. I think it's R2. Let me check it. Yeah, R2. Then we'll drill a hole, concentric hole. Right. So let's see, something like this. Right. So of radius R1. And of course this hole goes through the hole. Okay. So our material is only here. In the hole there is nothing. And it's uniformly charged. So we have infinitely long, uniformly charged hollow cylinder. So raw volume charge density given, and these two radii R1 and R2, so let me emphasize that this is a volume charge density.
Is it
Yeah.
large? Or-
Infinitely long. Infinitely long. Now I hate these sleeping modes in all these devices, because every time I have to check it down all the devices, right? On this guy, when I turn off the sleeping mode, it just stops recording, it's still awake, right, but it stops recording. Okay, yeah. Right. Okay, so again, we can use Coulomb's law, right? So this formula, no, I didn't write down the expression for the electric field created by a point charge, but that will be very, very complicated. So for this symmetry, the best law to use to find electric field is the Gauss's law. And let's find electric field in this shell, inside of this material. And this is a non-conducting material. Don't assume it's a metal, unless problem says that it's a piece of a metal or it's a piece of a conductor. Right. If it's a piece of metal, what will be the electric field inside? Zero. There would be any question, right? But this is a not conductor. Okay, let me emphasize. It's a non-conducting material. Non-conducting material. Maybe it's just some cylinder stuffed with charges, right? With potatoes, right? Yeah.
The whole part is not charged.
The hole, of course, it's empty. We just drill the hole, there's no material, there's nothing, no charges, empty. Right, okay, so let's start with the Gauss's law, of course. E dot dA Q enclosed over epsilon naught. And of course, as usual, the first step that we have to make before we can start applying Gauss's law, Gaussian surface. And of course, your Gaussian surface must be in the area where you want to find my electric field, and I didn't say that. All right, so let's find for R which is larger or equal than R1 and smaller or equal than R2. So we need to find the electric field in this part of the cylinder. Okay, so we need to pick a Gaussian surface. And of course, what will be the Gaussian surface? Which shape do we have to pick? Actually, it's not that we have to pick, right? You can pick any Gaussian surface, no restrictions. But since we want to solve this problem, we need to pick the best Gaussian surface possible for this particular symmetry, right? If you pick some crazy shaped surface, it will never be wrong. You will never be able to solve the problem. So what's the shape? Cylinder over some finite length L. Then that L, of course, will disappear. Okay, so let me pick a Gaussian surface. Everything will be in dash line because it's all inside. What? And so that's our Gaussian surface. Again, I use dash line because it's not supposed to be visible. Right. Of finite length L. Let's say L capital I use. And of some arbitrary radius R, which of course lies between these two values, R1 and R2. Right, so this will be R, some arbitrary radius R. And, okay, no, I will explain when we get to this point. Okay, so Gaussian surface, and so now let's start evaluating the flux, E dot dA. And so what do we have to do with this Gaussian surface? When we have spherical symmetry, the whole surface have exactly the same sort of type of surface, right? Now our cylinder has three different types of surfaces: cylindrical wall, flat, and flat surface over here. So in this case, if you try to integrate immediately over the whole surface, it will never work. But since the integral is an additive thing, you can split integral into as many integrals as you want. Right. So it means that this integral over this closed surface can be split into three integrals. Integration over cylindrical wall, integration over this flat surface, and integration over that flat surface, right? Right? Of course. So now let me, where's my, right, no, first I will label them. I will just label. So S1, cylindrical wall, S2, front surface or front facet, and this will be my back facet. Okay, so let me split it. It will be E dot dA over S1 plus integral of over S2 E dot dA plus integral over S3 E dot dA. Okay, I need to clear this part. So next, usually I ask students to draw electric field and area vector for each of these surfaces. Right? So let's start. Direction of the electric field. Radially out. Usually we justify that, at least in my recitation classes, I justify that, but on the exam, if you just draw the right direction, it's more than enough, right? So electric, let me pick some surfaces. Let's say this is the surface on the patch on the surface S1. Let me pick this surface, and let me pick, for example, here surface, right? So I will also show the direction of the area vector. So electric field, right, all the time, it's radially out. Electric field is radial. So that's the direction of the area vector for this patch. It's the same question like I asked you 10 minutes ago.
Yeah, no, it's
Ah?
90 degrees. Yes.
Radial, right, it's radial. Alright, so this will be my dA. Okay, that's dA for this integral, and now dA for that surface. For surface S2, that way, right? Okay. So this will be dA for front facet, and of course for back facet will be in the opposite direction. Because you remember convention for the Gaussian surface, area vectors must point outward. Okay, so now we can go back and start explaining the values of these integrals. So E is obviously for this surface S2 perpendicular to dA. Right? dA is radially out, area vector that way. Everyone sees that? Okay, so E perpendicular to dA. As a result, what's the value of the integral? Zero. Again, it's back to that formula, dot product, to cosine function which you asked. So it will be, I can write, so E dot dA equals E dA, you know what, let me write underneath, equals to E dA cosine theta. It looks like you're looking at the diagram confused.
No?
No? Clear about vectors, directions,
Yes,
right?
yes.
Okay, good.
Thank you.
All right, and let me write immediately the value of the angle, 90 degrees. Cosine of 90 degrees is 0. So that's 0. The whole thing is 0. And exactly for exactly the same reasons, the last integral is going to be 0. Yeah, because E is perpendicular to dA. Right, so as a result. Again, you could have told me from the very beginning, just using, applying sort of conceptual ideas. Why is the flux through surfaces 1, 0? Why? Conceptually, without going into calculations.
You have like dA on like opposite sides, so they kind of cancel out.
Not exactly right. In this case, they don't cancel. They just that 0, both that 0 and this 0, right? Idea is very simple. You remember again, what's the meaning of the electric flux? It's a number of electric field lines crossing a certain surface, right? Electric field lines are radially out. And these surfaces, they are parallel to these surfaces, this and that. So just physically, they cannot cross those surfaces, right? That's why that's 0 from the very beginning, without canceling. Or you can say 0, or you can say 0 cancels 0. It's not wrong. It just kind of sounds strange, right? But it's absolutely correct. Make sense? Okay, so this 0. So now let's take care of this. Let me separate like this. And so, and in this case, of course, E is parallel to dA. All right, the angle between them is 0. So E dot dA, it's E dA and cosine of 0 degrees. Cosine of 0 degrees, 1. E dA. Okay, so that's the explanation box for the first integral. So out of these three guys, only the first one contributes to the flux. So what we have, integral of E dA over surface S1, which is cylindrical wall. Next step. Because of the symmetry, what can you say about electric field on the surface of on the surface S1? Where is this one? Here, on this cylindrical wall. What's the value? What can you say about the value of the electric field? Strength, right? Electric field strength. It's very important, right? Because this is now just the magnitude, the strength of the electric field. Right? Constant, right? It's constant. Because electric field as a vector, it's not constant on that surface. Because you see, direction of the electric field. Over here it's this way, over here that way, directions are different. Right?
It's gonna be very...
It's not a bad camera, but sometimes I feel like we'll take 2 breaks, right? Okay, so somebody was asking something, sorry, right? All right, I have a good mood, right?
Like
Following the advice
give us
of
number values on the test or solving in terms of variables?
variables. I know you guys, some of you actually like really addicted to numbers, right? I don't like that your high schools make you addicted so much, right? I remember one student, right, he understood, right, and then just give me numbers. Yeah, you need to slightly be less dependent on that, right? So in this case, usually I don't give numbers. Or maybe at the end, if you derive the formula, I can ask you to plug some numbers, right? But of course not at the very beginning. So what? Now we found it. Let me check this just in case. I'm sure that it's right. Yeah, of course it's right. Okay, and now we just need to take it and plug it into that. Okay, so now let me rewrite at the bottom. Previous time, my former student, Sunip, was helping me because he could keep track of all these cameras, and now I have to do it by myself. All right, so let's finish this. So that is E times 2 pi r small times L equals Q enclosed is this. Rho pi L r squared minus r1 squared divided by epsilon naught. I just rewrote the Gauss's law with what we just found. You see L as it should be. L gets cancelled. Pi goes the same way. And that's it, right? So the rest we just need to arrange nicely. We will have E as a function of r small will be equal to rho r small squared minus r1 squared divided by 2 epsilon naught times r. It's a reasonably complicated relationship because our variable is in the numerator and also in the denominator. Yeah?
Could you rewrite rho as Q over V?
Q is not given. Why Q is not given? It's an infinitely long cylinder, right? Sort of you're talking about basically about infinite amount of charge inside, right? Of course, in real life, nothing is infinite, right? Everything has finite length, but with a very good approximation, quite often we can use this, right? For example, a rod of this length with this diameter, right? We can assume we can treat that as being infinitely long, right? If radius is significantly smaller. Okay, so that's the answer. Spherical symmetry you had in your quiz, right? And again, you cannot spend like 15 or 20 minutes, right? In my classes, students struggle for quite some time. You need to practice. You need to fly through the problem within like 10, okay, maximum 15 minutes, right? So practice, and as I said just a second, usually two types of symmetries we discuss: spherical and cylindrical. Yeah.
How much work do we need for each question so we can get like the full points? Because
If you answer each part, right, you will get full, right? I kind of find it difficult to answer, right? How much of work, so that everything is clear, right?
because it's not you're not just grading the exam by yourself. It's all.
We're not just grading answers, right? I fight with that, and some instructors do that, and I saw it in the past, and we had rough conversations, right? When I see just students write the right answer, but what was written above that doesn't make any sense. And the students, I remember, got 20 points out of 20, right? Of course, I went to the faculty, come on, you need to look carefully, right?
When we separate it into the three integrals, is it okay to just draw the vectors and then make the determination that it's equal to 0 instead of like writing that it's perpendicular and that the angle's 90?
As long as you can, as long as you explain why, you can say that the electric field lines are parallel to the surface, right? So it's obviously conceptually must be 0, right? Yeah, I can buy it. Right? But I usually ask, show me the area vector and electric field vector. Okay, so now enough of this, and you know what? Let me just bug you about vectors a little bit. If I can just start erasing this. You know what? Vectors will be at the end if you still have energy, right? Let me discuss problems which we, in some sections, we did not practice. So let's do this. We have 2 point charges, proton and electron. Let's say proton is fixed. Oh, somebody nailed it. So it cannot move. And the electron will be shot from infinity. So what we have to find, no, electron is, okay, initial speed is given. And we need to find the distance between these two charges. When the speed of this electron is twice as large as it had at infinity. Right, so let me draw the picture. And it will be easier to understand. So the next one, so we have electron and proton. So let me draw. So proton is over here. So this is a proton, and it's stationary. It means maybe it wants to move, right, closer to the electron because they feel attracted, right? Attractive force. But it cannot because it's fixed. Somebody holding it, right? Or something is holding it. Then electron comes from infinity. So this is an electron. And initial velocity V0. No numbers again. Don't be very disappointed, but so this is Q, and that is also Q. You remember proton and electron have the same amount of charge, but one of them is positive, one of them is negative. So this is positive and this is negative. Okay, so this is when R equals to infinity. Right, so that is initial situation. Let me write, so this is initial. So now let me draw final situation. So proton is still here, fixed. Right, so this is our plus Q. Of course, this electron keeps traveling, traveling, traveling. Is it slowing down or speeding up? Huh? Speeding up, because they feel a force of attraction. Right? So of course, speed goes up. And so eventually, we want to find this distance, RF. F stands for final, where the speed of the electron is 2v naught. Right? So that is the final situation, and this is initial and the final situation. Anything else? Just given? No. Maybe I can draw it like this. So this distance is r equals to infinity, and of course this distance is rf, which needs to be found. Initial velocity v naught, final velocity is 2 v naught. So which approaches can be taken to solve this problem? At this point, we can apply two approaches. The first one.
Force and kinematics.
Yeah, basically a force approach where you are supposed to use Newton's second law. Once you find acceleration, and if acceleration is, can we use when can we use kinematic equations?
When acceleration is constant.
Constant. And if acceleration is constant, we can use kinematic equations, right? But in this case, we have some troubles about that method. Second method, energy. So we're going to use energy. In this case, energy is easier. Right? So let's use our energy approach. And most likely in the problems, I will state which approach I want from you. If I don't say which approach to use, you're free to use whatever you feel like using, as long as you can solve the problem. Right? So what does it mean, energy approach? Total mechanical energy at initial moment of time must be equal to the total mechanical energy at the final. Basically, it's a physics 1 problem. With potential energy, the nature of the potential energy is an electrical, right? Just different nature. In physics 1, we were dealing with gravitational potential energy. Now we have electric potential energy. What's the big deal, right? So if you remember the right formulas, right? But the idea is exactly the same, right? So you shouldn't have. Usually students don't have significant issues with that. Anyone who practices this a little bit do well. Okay, so K initial plus U initial equals to K final plus U final. Formula for the kinetic energy, everyone remembers. Right? Again, it's in the formula sheet, but usually students, everyone remembers that. Expression for the potential energy, which expression must be used? That's why I asked, right? So, just wait. All right, so what can be used? Huh? Right, which formula must be used?
That one? Okay.
The whole word filled with formulas, right? Okay, guys, you need to understand that this formula is for the electric potential between point to point charges. This guy is one charge and it interacts with the capacitor or electric field, uniform electric field created by the capacitor. From time to time I see, not many but quite a few students use the wrong formula for the wrong system. All right. So So you need to realize this is for 2 point charges, this is for charge exposed to the uniform electric field, in this case created by a parallel plate capacitor. Right. Okay, so now let me show that we use kinetic energy, of course, 1/2 mv squared, and the potential energy equals to k q. Okay, let me write in general. Downstairs, the first power of R, because it's potential energy, it's not force. Now, for this formula, what's the value of the potential energy when the electron is at infinity? How do we call that point? It's a reference point, right? So potential energy, like in physics 1, gravitational potential energy, remember every time I was asking you, where is your reference level? At that point we had reference levels, now it's a reference point. So, okay, good. So it means that, what's the value of UF? No, UE, U initial. Zero. Okay, let me write here underneath to make it clear. So U initial equals K Q squared. Okay, you know what? No. Okay, let me ask you. I will ask you. Right. R goes to infinity equals 0. Strictly speaking, what is wrong in what I wrote? Actually, it will be 0 anyway, right? So okay, I will ask you then later that question. Right, so it will be 0. Right, so this is 0. Nothing else is 0. I thought at least kinetic energy can be counted. No, kinetic energies are not 0, right? Neither initial nor final. Okay, so now let's write explicitly. So initial, it will be 1/2 m v naught squared. Initial velocity is v naught given. Then this is 0 equals to 1/2 m 2 v sub 0 squared. And potential energy, K Q squared over R final. If I write it like this, right? Are you okay with what I wrote?
Why is the potential energy Q squared?
Charges are the same in absolute value. Q and Q,
Oh,
electron and proton, right? But what is wrong with what I wrote? On purpose I wrote this way.
The electron is negatively charged.
Ah?
Electron is negatively charged.
As a result, potential energy is
Negative.
negative. Potential energy is negative. Okay, on purpose I made this mistake, right, in order to emphasize on that. Okay, so now let me write explicitly. So it will be K, one charge is positive, one charge is negative, right, divided by R final. So potential energy is negative. Okay, so how many unknowns do we have in this equation? Mass of electron and no, everything is fine. First I almost my heart skipped a beat. I thought, wow, I couldn't believe that I thought about that I made a mistake, but everything's fine. Yeah.
I was just gonna say, I think you missed the charge on the final in the drawing, because I think it's supposed to be negative Q still.
Ah, okay, over here, yeah, we can do that. Right. So no, this is mass of which object? Ah? Electron. It's a mass of an electron. Maybe I should put a subscript E, because now we have these two objects. Proton, no, it's not a proton. Kinetic energy. Proton is stationary, right? Proton doesn't fly. Right. Yeah, how many unknowns? Which one? RF. The rest is given. Again, mass of these guys will be given in the problem if I give a problem about them. Or no, actually at the end in the formula sheet, all those numbers are given. Mass also. Right. Okay. So what? I will move this term to this side, right? And I will have 1/2 ME. You know what? No, I don't like moving that term. This term is negative, right? So let me move potential energy to this side, right, to make it positive, right? Okay. I changed the plan, right? I will move this term to that side, and this term will go to the right-hand side, right? It's more logical. Right, so as a result, KQ squared over RF equals M electron over 2 for V naught squared minus M electron over 2 V naught squared. We'll just move terms around. Right, then, of course, I can combine them. K goes downstairs, and Q squared goes there. So you're right. 1 over RF equals 1 over KQ squared, then ME over 2, and I will have 3 V naught squared. Right? ME over 2 I factored out, and actually V naught squared can be factored out, and we have 4 minus 1, so it's 3. And KQ squared from the numerator, it went down in the denominator on that side of the equation. Right? Diagonally moving factors. So now what we have to do in order to find RF, flip everything. So from here, RF equals to 1 divided by all that stuff. ME 2KQ squared 3 V naught squared. Okay, so the final step, let's just take everything which is in this very basement and goes upstairs, right? That's the rules of working with fractions. So we'll get 2KQ squared divided by 3 mass of the electron V naught squared. So that's how it goes. So pretty much at this point, it's just algebra moving terms around in order to solve for RF. So the second approach, which we started discussing, right? Force approach. What will be where are the troubles with that approach? Let me just quickly. Force approach. Of course, Newton's second law, right? So Newton's second law, right? So what we have? M times acceleration, right? Mass of the electron times acceleration equals to the force, electric force acting on the charge. What's the expression for the electric force?
KQ.
Coulomb's law, basically, right? Coulomb's law. ME times A equals K Q minus Q over R squared. You can solve it for acceleration. It will be, actually, you know what? It's let's look at the absolute value. Of course, minus plus is not a big deal. It's a direction, right? Just give us a direction of the acceleration. So KQ squared over ME R squared. Can we use kinematic equations?
No.
Why not? Why not? He said we cannot use kinematic equations. You sit next to him, right? I don't trust you. Why? Okay.
I didn't take physics one back to back, so I really don't remember.
You don't need. Okay, let's look at each term. K.
Okay.
What is K?
Constant.
Some constant. Charge. 1.6 times 10 to the power of minus 19 constant.
Yeah.
Mass of the electron, also tabulated constant, you can get it anywhere. What about R? Is it a constant number? Charge flies, R is getting smaller and smaller and smaller. R is not constant, acceleration is not constant, and kinematic equations bye-bye. You cannot use them. Yeah, you can, but it will be illegal, right? And your answer wouldn't make any sense. Because those kinematic equations were derived assuming that acceleration is constant. So it means that this will be significantly more complicated since these changes with R, basically it's a second order differential equation which you need to solve carefully. So energy approach in this case way better, easier, right? Sometimes energy approach or force approach, they're equally easy, especially if you are inside of the capacitor. Okay, not you, but the charge inside of the capacitor, right? Okay. So it's a not constant, and of course the saddest possible phase, right? Right, so exactly the same. Compare energies at 2 points, initial, final, whatever you have, right? And then carefully expand, look at what are zeros, right? And of course you have to pick the right formula depending on which system you have. And this problem is about a capacitor. Erase this. So next one. So we have charges in a capacitor. Which charges? Because I will show you now. So first, which orientation? Okay, here I will put a positively charged electrode. This will be my negatively charged electrode. So it's minus, 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 minus. Then this will be, of course, plus, 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 plus. And we have two situations. First situation, we'll take a proton. Of course, mass and charge is given, right? So first, we take a proton, and so what do we do with proton initially? We can release it. If you release it, it will start traveling by itself. Right? Okay, not by itself, but under the influence of attraction from that plate and repulsion of this plate, right? So V naught P, P stands for proton. Initial velocity of the proton, because there will be two charged objects, is 0, so it is released. And of course it will travel to the negatively charged plate, and the final velocity is given. So let's say V final of proton, and I can write so Vf of a proton equals to, finally you have numbers. Negative crosses capacitor, which is 50,000 meters per second, 50 kilometers per second. That's quite a speed. So that's first part of the problem, right? It's like a first experiment. You take a proton, you shoot it. Okay, not shoot it. You just release it. It travels. Final velocity, that one, right? And now let's take a helium atom, strip one electron, and now it will be, it has a charge of, the same charge as a charge of, proton. So now let me take helium plus. It's basically ion. You remember the first lecture we were discussing positive ions, negative ions. So it's just an atom of helium. You take one electron out. As a result, it becomes positively charged. So properties of helium plus. Mass, it's a full mass of the proton. And charge, of course, plus Q. And then proton, to compare proton, mass M, charge Q, okay, plus Q. So now we take this ion, and of course, again, we will release it. So V0 helium equals 0. Of course, it will travel, travel, travel. And we need to find the final velocity of this helium. So we need to find V, which way I label it, F. F helium. So first you shoot a proton, measured velocity, then you not shoot, release. Right. And then you do the same with helium. So we need to find velocity of the helium atom. Right, so let me check. I think, yeah, I used everything. What?
is that? Above
This? 0 helium. Initial velocity, right? Like here, 0 p, 0 because it's initial, p stands for proton, and here 0 again initial, helium, because it's a velocity, initial velocity. Right, in this problem, I think you can easily use force approach, and you can easily use also energy approach. I don't think that either of them is better or easier. They're equally easy. Right? They're equally easy in this case. Because all the time accelerations are going to be constant, and you're not going to end up with second order differential equation. Right? So you're going to end up using kinematic equations. Okay, so let's start using energy approach. Energy approach. So exactly the same. Compare energies at 2 points, initial and final. And how many equations we're going to get? This? Yes, of course, that formula is correct, but we don't have any information about the amount of charge on the plates, right? And as a result, and also we don't know anything about the area. But the thing is, if that is not given, it means that most likely, when you are going to solve it, you just don't need it. It's not needed. We will see, it will disappear, right? But that will be correct. But we don't have any information about the amount of charge. But since we have two situations, one for proton, one for helium, most likely those parts will just disappear. But anyway, so how many laws of conservation we'll have to use? I mean, not how many laws, how many times we have to use conservation of mechanical energy? Twice, one for proton, one for helium, and then when we have explicit, those equations explicitly in front of us, we can make a decision what can be done with those equations, right? But first, let's just E initial equals E final for proton, then the same for helium, and then we have two equations, and then we'll make a decision what can be done with those two equations. So let's start with the proton. So E initial equals to E final. And then the same for the helium. So let me write, so it will be K, I think I use subscripts. Yeah, let me use initial upper script P stands for proton. So that's kinetic energy, initial kinetic energy of the proton plus initial potential energy of the proton equals to K final proton plus U final proton. And which formula for the potential energy?
Potential energy, QES.
Yeah, QES. S is the distance from what?
From negative capacity to positive.
What?
Negative to
from the negative electrode, right? When we derive this formula, our S, actually I showed it, right? Right, so S is measured from the negative electrode. You just need to remember. It means that the reference point is at
0 at the negative.
negative electrode, of course, right? Okay, so now let me show that this U equals QES. All right, QES. And of course, let me show that this is S. And this is S equals 0, right? So, initial 0. It's conflict. So because V0P equals to 0. Right? So what else? Initial proton, where is initial? It's not 0, right? What about the final potential energy of the proton? That is 0, because S will be 0. Okay, so now let me write, so it's a Q, E, and S. S is 0. So that term is 0 also. Okay, it's a nice simplification, I like it. And of course, this will be Q. It's a proton, so no troubles with the sign. Q, E. What's the value of S at the initial point for the proton? It's some spacing between the plates, which is, again, not given. Like charge is not given, spacing between the plates is not given. It just basically means that at the end we will not need them. But when they're going to disappear, we will see. But for now, we just need to introduce it in order to go through this solution smoothly. Again, it's not given. These are not given. So both E and D are not given. Right? So I just want to emphasize, but I introduce it in order to have a nice solution. I need them. So yeah, this is 0, right? And final 1/2 mass of the proton times final velocity of the proton is given F, P is given squared, right? Okay, so now let's leave it, because right now there are too many unknowns in this equation. So let's dive it in the second. Let's dive for the second equation. All right. So now let's look for helium. Right. Again, E initial equals to E final. Maybe I'll split this. So now similar approach, but now for the helium. Again, K. Initial helium plus U initial helium equals to K final helium plus U final helium. So is it coming back? Energy approach? Yeah, of course, it's one of the easiest part. It's not like angular momentum or torques or the rotational need at second law where students go, oh, what is that? So the same zeros, right? Initial, because we do basically the same, it's just a heavier object, right? So this is 0. This is also 0 because of the same thing. Yeah, now let's write the rest. Charge of the helium. Exactly the same. We stripped 1 electron as a result. That helium ion charged with plus Q, right? Just 1 extra proton inside of that atom, right? So the same charge. Q, plus Q, plus Q. Electric field still the same because they're traveling through the same electric field, right? It's uniform, exactly the same. And since they travel through the same capacitor, D is the same. Now you see how these E and D are going to disappear, right? Q, E, D equals to final, okay, 1/2 mass of the helium times velocity of the helium final, which we need to find eventually, right? That's the question. So that's our ultimate goal, to find that velocity. So that's our equation number 1. This is equation number 2. QED are the same on both sides. So it means that you can just combine those two equations right together. Okay, let me erase the rest. This. So I will put an arrow. I'm combining these two equations, which is obviously, right, QED the same on both sides. So I can write, first I will write this 1/2 mass of the helium. Velocity final of the helium equals to, again, 1/2 is going to disappear. Mass of the proton, velocity of final of the proton. Of course, 1/2 goes. Mass of the helium, it's a 4m. Right? So we're all inside. Right, so, okay, let me show that this is 4m. Okay, anyway, so let me write V final of the helium equals square root mass of the proton, mass of this ion times velocity, final velocity of the proton, square root. Now just simple manipulations. What?
Why did you equate though?
Huh?
Did you add the two equations?
No, I didn't add. Look, the right hand, or no, left hand side, QED, QED. They both equal to the same, so it means this is equal to that, right? So that's what I wrote here. That's why I put this kind of bracket, right, combining these two equations. Right? Awesome. So V final can be, of course, factor. I mean, we can take it outside of the square root, and so we have m over 4m. Is it right? Let me check my notes. Yeah, divided by 2. So it will be V final of the proton divided by a factor of 2. So this velocity is 50, so divided by 2 it will be 25,000. 25,000 thousand meters per second. Yeah.
Just confused as to why is helium 4n?
Given.
That'll just be given?
Yeah.
Okay.
If you strip one electron, right, so it will be charged with one charge of the electron, and the mass is just 4 masses of the proton, right? So it's given, right?
Is there a difference between QES and QED?
Okay, say it again.
The formula we get QES, is that different from QED? Is QED just particular to the problem?
QED, no.
QES on the left.
QES on the left. I mean, this, no. This S, it's a variable, like X. Right, X can be anything, right? 0, 1, 2, 3, 4, 5. And then D, it's a particular number. Maybe let's say 3 meters away from the origin, right? So D, it's a particular value of S.
Okay.
Right, don't ask me why the author used S instead of X, right? His minor compulsion, right? So S, again, you understand, right? It's a variable, but D, it's a particular value of that variable.
But they're both U.
Both U, no, that they part of the U, right? QES, right? So S, it's a variable. You see S. So 0 here, and then blah 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 blah. This is D. Yeah, I should have probably shown that. This is S equals to D. D, it's usually distance between the plates, right?
Yeah.
Okay. I just didn't feel like applying conservation of mechanical energy for just one charge, right? So I just combined two, but I just put 2 charges together. Just to make this problem at least a little bit more challenging, right? Otherwise it will be just so banal, boring. Okay, any other questions? So it's 8, slightly more, 2 hours, 10 minutes, right? Let's just final conceptual question, right, and call it a day. Vectors, reviewed at the very beginning those problems about finding the net electric force, right, on net electric field, right? It's so boring, as I keep saying, working with those vectors, right? And of course, here's additional problem of this type. If we start discussing it, it will take another like 20 minutes. The last conceptual question. Okay, I'm not going to erase it. Let me just separate it this way. So what if we have, for example, this situation, we have a positive charge, let's say Q capital. And let's shoot a electron. So let's say electron travels this way. Let's say this is a trajectory of an electron. So E minus, so that is an electron. And it travels that way, you see. Direction is shown. What can you say? What happens with potential energy of this system as electron travels? Is potential energy going up or down?
Down. It approaches zero.
Approaches zero. You can approach zero from this side, from that side, right? You can be down, yeah, down is, but approaching zero, you can approach from two different sides, right? So first of all, potential energy, is it positive or negative? What are you talking about? Okay, it's a system of 2-point charges. And I asked the question about the potential energy. So we need to go to our database and find the expression for the potential energy of 2-point charges, right? Which is that? This is potential energy of a charge inside of the capacitor. That's what we used in the previous problem. It's just not our case, right? That's potential energy of 2-point charges, right?
Relative to the negative one, right?
Okay, now first we need to identify which formula we have to use, right? So U equals K Q capital. Okay, let me just write in general, so with R, first power. So that is just a formula, let me frame it, right? And now let's write explicitly for our case. So it will be U equals K Q minus Q divided by R. So potential energy is negative because an electron is negative, right? So now after this you should be able to tell. So what actually happens with potential energy? Is it is it increasing or decreasing as electron travels along that trajectory? Increasing. Decreasing. Approaching zero. You still stand up there.
Approaching zero from the negative.
Okay, so now you are more specific, right? Okay, now let's start analyzing. First of all, potential energy is negative. Negative. Right? But then, as electron travels, what happens with R?
The denominator's getting bigger.
R is getting bigger, right? So you see R first, it's this smaller, then it's getting longer and longer and longer and longer, right? R is getting bigger. And R is in the denominator. So what happens with the absolute value of the potential energy? Decreasing. Absolute value. Absolute value. One step at a time. So absolute value is increasing. But since it's negative, so potential energies become more and more negative, right? So more and more negative, it means what happens with the potential? Is it more negative? Am I right?
Less and more.
Huh?
Like less and less. Like the smaller gets.
Yeah. No, I just he was so he was trying to convince me that it's approaching zero, right, from a negative. And now since he was so confident, now I started doubting myself, right? So R is increasing, right? So this is getting smaller in absolute, increasing absolute smaller, right? Smaller, right?
Yeah.
Right. So it's getting smaller and negative, right? Damn, so he's right. He's right. Okay, so you see? Okay, so R increasing, okay, increases. So as a result, absolute value of the potential energy decreases. Again, you see absolute value. But since U is negative, so it means that potential energy is getting less and less and less negative, right? And wait. And U is negative. So potential energy becomes less negative. Becomes less negative. So if you plot potential energy, for example, versus R, let's plot this. So this is potential energy, this is R. So first, when R is small, potential energy larger in absolute value, but of course more negative, so it means it's smaller. Out of two negative numbers, the one which is less negative is larger, right? So you will have something like this. So it becomes less negative. It's a long day. But I trusted you, so that's why I started doubting myself, right? Because you're so confident. Okay, I think it should be enough, right, to refresh everything. Right. If you have any questions here, you can ask. Right. As I said, in my classes, in my recitation classes, we haven't started discussing practicing this conservation of mechanical energy. So I'm planning to do it on Tuesday because guys on with recitation classes on Monday. Okay, whatever. It's so long.
ei mere viisa tule, viipsin tyt se kohut